I'm pleased to present the BIONANOCAR project and the preliminary result of this project. BIONANOCAR aims at exploring two different strategies for better exploitation of the radiosensitizing effect of ultra-small gold nanoparticles. Einfeld and his colleagues demonstrated in a famous paper published in 2004 that the ultra-small gold nanoparticles permit to increase significantly both the contrast of image acquired by X-ray imaging, by CT imaging, and the efficiency of the radiotherapy owing to the strong radiosensitizing effect of the gold nanoparticles. This study opens probably this study is probably at the origin of the intense research activities devoted to the development of radiosensitizing gold nanoparticles for image-guided radiotherapy. Image-guided radiotherapy is very attractive because it is expected to improve the selectivity of the radiotherapy. Indeed, the irradiation can be induced when the biodistribution of the gold nanoparticles after intravenous injection, monitored by CT imaging, is adapted for, at the same time, eradicating the tumor and preserving the healthy tissue. So, the success of this strategy rests on the preferential accumulation in the tumor, monitored by CT imaging, as shown here, and also on the removal of the excess of the nanoparticles. And in the case of non-biodegradable nanoparticles, renal clearance must be preferred. As a consequence, the hydrodynamic diameter of the particles does not exceed 10 nanometers. Moreover, the studies performed by the research group of Fred Currell and Kevin Price demonstrated that the radiosensitizing effect is more intense for the smallest gold nanoparticles. And this conclusion is very stimulating for the clinical application of the gold nanoparticles for radiosensitization, because the most efficient ones for the radiosensitization are also the most suited for the renal clearance, which is a prerequisite for the in vivo application of non-biodegradable gold nanoparticles. And since, owing to its ionizing character and its low sensitivity, CT imaging, X-ray imaging is probably less suited for the image-guided radiotherapy than magnetic resonance imaging, than MRI. But the follow-up of the gold nanoparticles by MRI requires the presence of gadolinium chelates onto the gold nanoparticles. In this context, we developed the synthesis of gold nanoparticles coated with linear or microcyclic polyamino carboxylate chelators by adapting the Bruce protocol. This protocol is very well suited for providing ultra-small gold nanoparticles with a high colloidal stability in aqueous solution. The reduction of the gold salt by sodium borohydride in presence of these polyamino carboxylate chelators yields gold nanoparticles coated with these chelators. And the core size of these particles is 2.4 nanometers, and the hydrodynamic diameter of these particles is comprised between 6 and 8 nanometers. So, owing to the small size of the hydrodynamic diameter, these particles are expected to be removed from the body by the renal clearance. Moreover, the chelating properties of the organic shell is expected to ensure the immobilization of gadolinium ions, for instance, for the follow-up of these particles after intravenous injection by magnetic resonance imaging, by MRI, instead of by CT imaging. The chelator-coated gold nanoparticles are composed of two parts, of two different parts, but with complementary properties, the organic shell and the gold core. The organic shell confers to the particle a high colloidal stability in biological media and long-term immobilization of gadolinium ions in the organic shell for a follow-up by MRI, and also of radioisotopes such as indium or technetium for a follow-up by nuclear imaging. While the radiosensitizing effect and the CT imaging stem from the gold core. Finally, the small size of the gadolinium chelate-coated gold nanoparticles and the surface properties plays a decisive role in the control of the biodistribution of these particles after intravenous injection, as shown by this image acquired by nuclear imaging and by MRI. The gold nanoparticles after intravenous injection freely circulate since no undesirable accumulation is observed in the healthy tissue except in the organs involved in the renal clearance, the kidneys and the bladder. But when these particles are administered to rats bearing a brain tumor in the right hemisphere, we can observe a preferential accumulation of these nanoparticles in the tumor as revealed by the contrast enhancement, the positive contrast enhancement in the brain. This preferential accumulation was exploited for increasing the lifespan of the animals of the rats bearing a brain tumor. And when these animals are treated by radiotherapy 10 minutes after intravenous injection of these gold nanoparticles, we can observe a longer survival of these rats in comparison to the rats of the control groups. So the gadolinium chelate-coated gold nanoparticles exhibit a high potential for image-guided radiotherapy. Oops, sorry. But this potential is underexploited because of a too rapid renal clearance. Since the too rapid renal clearance is suspected to limit the accumulation of the gold nanoparticles, of the ultra-small gold nanoparticles in the tumor, the strategies for postponing the renal clearance deserve to be explored. And the main strategy for achieving this goal could consist in using larger gold nanoparticles, but this strategy is not satisfying because the renal clearance of the particles is restricted to the case of particles with a hydrodynamic diameter less than 10 nanometers. For achieving, I will try again, okay. For achieving a better targeting, while preserving the renal clearance of these gold nanoparticles and the radiosensitizing, the strong radiosensitizing effect characteristic of the ultra-small gold nanoparticles, we propose in the framework of BIONANOCAR to use superparamagnetic magamite nanoflowers and polymeric PLGR particles as large and biodegradable carriers. These carriers are expected to ensure an enhanced vascular residence time after the intravenous injection because these particles are too large for renal clearance. However, the renal clearance of the gold nanoparticles will be preserved but postponed because they will be released after the biodegradation of the nanoflowers and of the PLGA particles. The nanoflowers are composed of magamite grains with a size of 11 nanometers, which are assembled in a flower-shaped structure. And the grafting of the gold nanoparticles onto these nanoflowers, hereafter called golden nanoflowers, okay, is very attractive because each part of this multi-component nanostructure will be designed in order to play crucial roles in the control of the biodistribution in imaging and in therapy. For instance, the role of the magamite nanoflowers will not be limited to the transport of the gold nanoparticles. Indeed, due to the superparamagnetic characters of these magamite nanoflowers, they behave both as negative contrast agents for MRI and also, eventually, as nanoheaters for hyperthermia. So, the immobilization of the gold nanoparticles onto these nanoflowers is interesting because it permits to combine radiosensitization and hyperthermia with higher vascular resistance time. The grafting of these gold nanoparticles onto the nanoflowers was successfully performed by using dopamine as a linker. The presence of amine function in this molecule, in dopamine, and of a large number of carboxylic acid groups in the organic shell renders possible the functionalization of the gold nanoparticles via the formation of an amide linkage. As a result, the gold nanoparticles were decorated with the catechol moieties, which exhibit a great affinity for the iron oxide surface. After magnetic sorting, golden nanoflowers with a size between 25-30 nanometers were obtained. And the higher accumulation of the gold nanoparticles, when they are carried by nanoflowers, was confirmed by post-mortem gamma counting of organs and tumors after the intravenous injection of the radiolabeled gold nanoparticles and the radiolabeled golden nanoflowers to rat bearing a brain tumor. Whatever the case, the amount of the gold nanoparticles in the tumor is higher than in the healthy tissue. The tumor is represented by the orange bar, because since the ratio of radioactivity between the tumor and the healthy tissue is higher than 1. But this ratio is higher in the case of the golden nanoparticles carried by the nanoflowers. So we can conclude that the nanoflowers behave as efficient carriers for the ultra-small gold nanoparticles. And the preferential accumulation in the tumor was exploited for increasing the lifespan of rat-bearing brain tumor. When the animals were treated by radiotherapy 10 minutes after the intravenous injection of the golden nanoflowers, the purple curve here, we observe longer survival of these animals in comparison to the animals of the control groups. The encapsulation of the gold nanoparticles, the same than those used for the synthesis of the golden nanoflowers, in PLGA particles, is the second strategy explored in BIONANOCAR. The encapsulation, which was performed by a novel route, was recently patented. And like in the case of the golden nanoflowers, the PLGA particles, the role of the PLGA particles is not limited to the transport of the gold nanoparticles. Indeed, we demonstrated that it is possible to co-encapsulate the gold nanoparticles with an anti-cancer drug. And this co-encapsulation is very attractive because it permits to combine chemotherapy, radiotherapy, with a higher vascular resistance time. And the PLGA particles containing the gold nanoparticles can be followed up by MRI as revealed by the positive contrast enhancement in liver during the first 20 minutes. And the pharmacokinetic studies revealed that the gold nanoparticles exhibit a higher vascular resonance time when they are encapsulated in Pelger particles, in contrast to the non-encapsulated particles. In conclusion, although the results are very preliminary, the BIONANOCAR project shows that it is possible to improve the vascular resonance time and to better exploit the radiosensitizing effect of the ultra-small gold nanoparticles, thanks to the grafting of the ultra-small gold nanoparticles onto the nanoflower, or thanks to the encapsulation in the Pelger particles. Thank you for your attention. I would like to thank the funding agencies and all my colleagues who are involved in these projects. Thank you very much.
Thank you very much, Stéphane, for this nice talk. So is there any audience in the question in the audience? I have one. So you show that the nanoflowers at the end are interesting because then you can have this magnetothermic effect, the heat that you can apply to this. But did you in your assay, I didn't figure out whether you have assessed also your 10 nanometer particles compared to the nanoflowers to see the difference with the irradiation. So you didn't compare the previous particles that you showed in your talk.
I don't understand everything, but
so first of all, you showed that 10 nanometer particles are interesting for radiotherapy, yes, right? And then you switched to the nanoflowers, but you didn't include those first nanoparticles as a control. So if you would put these nanoparticles as a control in your rat model of brain cancer, what would be the survival rate of these rats compared to the nanoparticles?
I'm not sure.
Nanoflowers, I mean.
You say you want to know if we compare the nanoflowers without gold nanoparticles and nanoflowers with gold nanoparticles? I'm not sure.
Yes.
Okay.
Yes.
Yes. We did this comparison, and the golden nanoflowers are more efficient than the nanoflowers without gold nanoparticles,
right,
for improving the survival of the rats.
Okay, but at the same time, you also mentioned that the 10 nanometers nanoparticles are better for radiation, right? So, and they work better. So, and the smaller, the better. So we would have expected to have the other way around, wouldn't we?
Mm-hmm. 10 nanometers, the gold nanoparticles of 10 nanometers, you say? I don't understand.
Yes, you have an effect with your,
we did not this comparison because gold nanoparticles with 10 nanometers, with a diameter of 10 nanometers.
No, they are not gold nanoparticles. These are, gold nanoparticles of 10 nanometers, yes, right.
Yes, cannot be removed by renal clearance. And for us, it is, you can use those particles because there are no future for clinical applications. Okay? And the renal clearance is very prerequisite for the use of the particles. And in the case of the gold nanoflower, the size is larger, okay, but they can be altered in the body. And after biodegradation of the golden nanoflower, of the magamite nanoflowers, the gold nanoparticle can be released, and after they can be removed from the body by urine. Okay, so for us, the small size of the particles, of the gold particles, is very important.
Okay. One short question to conclude. What is the field of application regarding cancer? What kind of cancer do you expect to treat preferentially with this kind of approaches?
We are interested in brain tumors.
Okay, so it can reach the brain and.
Well, yes, you can. With animal models, we demonstrated that it is possible to target the brain tumor
Okay.
with those particles. But we are interested also in another tumor, for instance, pancreas.
Liver cancer?
Sorry?
Liver cancer?
Liver cancer, it's not easy, liver cancer, because those particles were formulated with the objective to avoid liver.
Okay.
Okay, so it's a difficult.
Okay, thank you very much.
Thank you.
Okay.